Okay, so here are your formulas for the derivatives of the other of all of the six, actually. So here are the six formulas for the derivatives of arcsine function. And again, you can get those formulas by following the example that I gave you up here on these two problems, where I actually took applied the function to both sides to eliminate the arc function. So, and then you can use a right triangle. So I'll just leave you to prove the other four. But basically, if we wanted to apply these derivatives, okay, so let's say we wanted to find the derivative of arcsine of 2x. Well, in this case, the u would be 2x, right? So the derivative of arcsine would be this one. So I would actually have u prime. Well, u prime would just be 2. So I would, a couple ways you can look at this. You can say I'm going to do 1 over this square root and then times u prime, or you can just do u prime over this square root. But I kind of like to do it this way: 1 over the square root of 1 minus u squared. Well, what's u? U is 2x. So it'd be 1 minus 2x quantity squared in the square root. And then you multiply by u prime, which of course is just 2. So when you simplify that, you're going to get 2 over the square root of 1 minus 4x squared for the derivative. Now, here's one for finding the derivative of arctan of u. And again, here u would be x squared, and then of course du would be 2x, or I'm sorry, u prime would be 2x. So u would be x squared, and then u prime would be 2x. Okay, so now let's look for the derivative of arctan of u. Okay, that's right here. So you're going to have 1 over 1 plus u squared. So that's going to be 1 over 1 plus x squared squared, and then times the derivative of u, or u prime, which is 2x. So then when you simplify that, you're going to get 2x over 1 plus x to the fourth. Okay, so this time I'm going to take the derivative of arcsecant of u, where u is natural log of x. And of course, if u is natural log of x, then u prime would be 1 over x. So for arcsecant, that's a little more complicated. Here it is right here. So you're going to have 1 over the absolute value of u. So that would be 1 over the absolute value of u. So it would be absolute value of natural log of x. And then this times the square root of natural log of x, or u squared, minus 1. So that would be natural log of x squared minus 1. And then of course you multiply by u prime, and here's u prime 1 over x. And so once you put all that together, if you multiply that 1 over x by this fraction, you're actually going to get 1 over x times the absolute value of natural log of x times the square root of natural log of x squared minus 1. And so that's how you can apply those formulas to find derivatives involving inverse trig functions. Now you can use calculus to analyze inverse trig functions. Like here we have y equals arctan of x squared. And you know that if you let x be 0, then tangent of 0 is 0. So that would give me that when x is 0, y is 0. So we would get an intercept of 0, 0. Now the first derivative of this can be obtained from the formula, and I actually did it right here. So it's 2x over 1 plus x to the fourth. So there's the first derivative. Well, that's going to have a critical number at 0. So if you test to the left of 0 and test to the right of 0, or maybe you could just use the second derivative test, but either way, if you use the first derivative test or the second derivative test, what you should find is that to the left of 0, the function is going to be decreasing, and to the right of 0, the function is going to be increasing. So that means that that point 0, 0 is a relative minimum. And now if you get the second derivative, then the second derivative is actually, you'd have to apply the quotient rule to the first derivative, and you're going to get 2 times 1 minus 3x to the fourth over 1 plus x to the fourth. I can't remember, that might supposed to be squared there. I would imagine it is. I'll have to check that and make sure. Yeah, this should be squared, so it's 1 plus x to the fourth quantity squared down here. Okay, but if you want to find possible points of inflection, you'd set this equal to 0, and so this would be equal to 0 when 1 minus 3x to the fourth equals 0, or x to the fourth equals 1/3. So x would equal plus or minus the fourth root of 1/3, which is about plus or minus 0.6. And further testing around these two x values, minus the fourth root of 1/3 and plus the fourth root of 1/3, you can determine using your test for the second derivative, well, your concavity test for concavity, you can determine that the graph is going to be concave down from negative infinity to minus 4 square root of 1/3, or minus fourth root of 1/3, and then also concave down fourth root of 1/3 to infinity. So basically here it's got that concave down, see that concave downward action, and then over here it's got that concave downward action, even though I know it's not turning down, but I'm just trying to emphasize it for you. So it's got the downward action outside of those 2 points. Now I just estimated the 2 points right here and here, so those are the 2 points. And then between the 2 points, it's concave up between them, and another error there, so copy and paste kind of gets me sometimes. Okay, so that's concave up on the interval between the two. And so what that tells me is that at minus the fourth root of 1/3 and f of minus fourth root of 1/3, well, actually, if you plug the minus the fourth root of 1/3 into the function, the original function, what you're going to find out is that that's actually going to be pi over 6 for the y value. So this point here is minus fourth root of 1/3 pi over 6, and so that's the point of inflection. And then the point fourth root of 1/3 and f of fourth root of 1/3 is actually going to be, there's another typo there, and is actually going to be fourth root of 1/3, and it's also going to have pi over 6. So that's going to give you this point here for your point of inflection. And remember, the point 0, 0 here was actually a relative minimum. So basically, by knowing those 3 points, we're able to generate a portion of the graph by knowing that we're concave down here to this point, and then we're concave up to here, and we hit a minimum, and then we're increasing concave up here, and then we switch back to concave down. And so by knowing that information, we're able to generate a graph of this function y equal arc tangent of x squared. Okay, I'm going to finish this with an application involving arc functions. So a photographer has taken a picture of a painting hung in a gallery. The painting is 4 feet high. The camera lens must be placed 1 foot below the lower edge of the painting. How far should the camera be from the painting to maximize the angle subtended by the camera lens? Okay, so I drew a picture over here. Here's the painting. Okay, and this actually is the camera. The camera is right here. And so notice the camera lens is placed 1 foot below. So the camera lens is right here. This green line is the camera lens, and it's placed 1 foot below the painting. And it says how far should the camera be from the painting. So basically we're looking for x here, the distance of this green segment here, x. And we want to maximize the angle subtended by the camera lens. So let's let theta be the angle between a line that would connect the bottom of the picture to the top of the picture, and let's let theta be that angle. And then let's let alpha be the angle between the camera level and the bottom of the picture. So alpha would be this angle, and then we would want to, let's see, beta is going to be the entire angle from here to here. Okay, so that's going to be beta. So basically what we want to do is we want to maximize this angle theta here, but theta is actually the angle beta minus this angle here alpha. So we can write theta as beta minus alpha. Now, since this is a right triangle here, let's see, and we know that we can say cotangent of beta is x over 5. So since beta is this entire angle, well, tangent is opposite over adjacent. So cotangent would be adjacent over opposite. So that would be adjacent for beta would be the x, and then the opposite would be all the way to the top of the picture. And since the picture is 4 feet, then that would be 1 foot plus 4 feet is 5 feet. So cotangent of beta would be x over 5. Now, cotangent of alpha, playing it the same way, alpha, the adjacent angle would be x, but the opposite angle, the opposite side of that would be 1. So the adjacent side would be x, and the opposite side would be 1. So cotangent of alpha is x over 1. So basically, we know that if we hit both of these equations with arc, like here, if we take the arc cotangent of beta, then we're just going to get beta, and on the right side we'll have arc cotangent of x over 5. So in other words, we're able to solve for beta. And here, if we hit both sides of this with arc cotan, we get alpha on the left, and we get arc cotan of x on the right. So now I've got beta and alpha in terms of x. So now that I can go back to this theta equals beta minus alpha, and I get theta here is equal to the arc cotangent of x over 5 minus the arc cotangent of x. Well, now I can take the derivative of theta with respect to x, and you'll have to go back and look at your formulas for the derivative of arc cotan, but basically it's 1 over 1 plus u squared, and then times the derivative, actually it's times minus the derivative of u, or minus u prime. So you have minus u prime over 1 plus u squared, and then the same thing here. You have, but you're going to have minus a minus u prime. Now u prime here is just 1, so you're going to have minus 1 over 1 plus x squared. And then let's see, what can we do there? We can, minus a minus is going to be plus. I went ahead and multiplied the top and bottom by 25. So then I did a little algebra after I did that, and I got a common denominator. And then when I got a common denominator and collected like terms on the top, I got minus 4x squared plus 20 for the numerator. And then the denominator was 25 plus x squared over 1 plus x squared. And then, remember, now we can just set the derivative equal to 0 and solve it. And it turns out if you solve this equation, you get x squared equal 5. So that means x must equal the square root of 5, because it can't be the negative square root, so it's got to be the positive square root of 5. So x should be about 2.236 feet, or about 2.24 feet. And, you know, that's an example of using these inverse trig functions. Now, I'll leave you with this picture that basically covers all the differentiation formulas that we've hit up until this point. And so if you want to take a snapshot of that or freeze the video, feel free to do so. But those are the differentiation formulas that we have up through this point.